Okay, geometry students, today we're reviewing Unit 5. Unit 5 was kind of the point where we stopped talking so much about different properties of geometry in general terms and started applying them to specific shapes and polygons. And we started off with one of the most common figures in all of geometry, and that is the right triangle. Okay, so anywhere we have right triangles, we know that we have all kinds of special rules that go along with the right triangles, and one of them would be the Pythagorean theorem. Okay. Now, basic vocabulary as far as the structure of the right triangle is concerned. The two sides that build the right angle are what we refer to as the legs of the triangle, and the side that is across from the right angle is what we call the hypotenuse of the triangle. The hypotenuse is always going to be the largest side of the triangle, and that's important because when it comes to the Pythagorean theorem, you absolutely have to make sure that you plug the hypotenuse into the correct location. And as we kind of started to see for one of the first times is that most of our rules in geometry and most of mathematics are written in conditional format. If P, then Q. Okay, well, our hypothesis in this case is we have a right triangle. If we have a right triangle, then the conclusion is then a squared plus b squared will in fact equal c squared. So the Pythagorean theorem effectively relates the three lengths of the sides of a right triangle to each other. A squared plus b squared equals c squared. And obviously, you got to get the, it doesn't matter which of the legs or which of the two legs you plug in for A and B, but you got to get the hypotenuse in there correctly. So we talked about the basics, how you solve for the variables in the Pythagorean theorem. And of course, since all of our variables are squared, that means we're going to have to use square roots in order to get the square off of the variable. And we introduced a brand new term. If you have a right triangle and all three side lengths end up being whole numbers, that's kind of a rare case, and that's what's called a Pythagorean triple. Okay, the rest of this was all just examples, I believe, for the first day, and that was that. The next day we turned around and we looked at the converse of the Pythagorean theorem. Okay, so reviewing converse takes your hypothesis and your conclusion and reverses them. So instead of saying if you have a right triangle, then a squared plus b squared will equal c squared, now we are saying if a squared plus b squared does equal c squared, then you must have a right triangle. Okay, so now what we're doing is we are using the three sides in an unknown classified triangle to determine if it is a right triangle or not. So when you plug in your three sides of your triangles, again, still making sure you get the hypotenuse in the right position in your Pythagorean theorem. If a squared plus b squared does in fact equal c squared, then that means you must be looking at a right triangle. Okay, we looked at a couple of examples, and then we kind of opened up our thinking a little bit and said, all right, if a squared plus b squared does equal c squared, then that must be a right triangle. But what happens if a squared plus b squared does not equal c squared? That means that either the sum of the two legs being squared is larger, or possibly the hypotenuse is larger. But in either case, our equality becomes an inequality, and the scales of the equation tip one direction or the other. Okay, and we need to understand when it tips a particular direction, either towards the legs that are being squared and added together or towards the hypotenuse being squared, that means something. And we talked about it in class, kind of a way to think about it, and I typically base it all on the hypotenuse. I like to think about the hypotenuse because it's got its own side of the equation, so that's just one thing to consider. Okay, so what I think about is this. If that hypotenuse sitting by itself, being squared, is not heavy enough to win the battle on the scales, the two little sides being squared and added together, they won the battle over the largest side being squared. To me, that tells me that the hypotenuse must not be very big if it's losing that battle. And of course, we know that in a triangle, the side lengths and the angles across from them are related. So what would you expect to find across the triangle from a small hypotenuse? We would expect to find a small angle, and our term for small angles is acute angles. Okay, so small hypotenuse means small angles means acute. So that would be an acute triangle if a squared plus b squared is bigger than c squared. Now, the opposite side of that argument is true as well. Let's say the hypotenuse being squared wins that battle all by itself. C squared is bigger than a squared plus b squared, so the scales tip towards the hypotenuse. To me, what that says is that hypotenuse must be a big hypotenuse, and if you look across the triangle from a big hypotenuse, what kind of an angle would you expect to find? A big angle, and our term for big angles is obtuse angles. Okay, so if a squared plus b squared is smaller than c squared, then that means we have a big angle. That is an obtuse triangle. Okay, so it's not only important to know that a squared plus b squared equals c squared to make a right triangle, you also got to understand which direction makes it acute and which direction makes it obtuse. Okay, so we looked at some more examples of those, and that was it. A couple days later, we came back and we looked at special cases of triangles. There are two triangles that we call special right triangles. They are the 45-45-90 and the 30-60-90. And these numbers refer to the interior angle measurements of those triangles. Okay. Now, the reason these are called special right triangles is because their side lengths are predictable based upon what other information is going on in the triangle. And that's no great surprise. We found a lot of relationships inside of right triangles. This is just a couple of them. Okay, now the short of the 45-45-90 is that if you have two angles that are congruent, being the 45 and the 45, that means that the two sides that are across from them must be congruent as well. That's why you have the tick marks down at the bottom of the screen. Okay, so two sides of our triangle are going to be the same, and then the hypotenuse, which is bigger, will obviously be a different measurement. Okay, so basically here's what we're saying. If we're saying that our legs of our triangle are some unknown value, x, okay, then the relationship that exists in a 45-45-90 is that the hypotenuse will be whatever the length of the legs are times the square root of 2. Okay, so after you establish that you have a 45-45-90, then the hypotenuse is always leg times root 2. So if you know your leg, you can just multiply by the square root of 2, and that'll give you your hypotenuse. If you know the hypotenuse, you can just divide by the square root of 2, and that will give you your legs. Okay. There was a couple of examples in there. You can look back at those if you need. And then the 30-60-90. Now, once again, that refers to the interior angle measurements, 30 degrees, 60 degrees, 90 degrees. We picked up a little bit of extra vocabulary for the 30-60-90. We cannot call both of the legs just leg in the case of the 30-60-90 because actually one is larger than the other. So we have vocabulary that specifies short leg and long leg, and that should be very easy to determine which one is which because, of course, the short leg would be across from the smaller angle measurement, which would be the 30. The long leg would be across from the medium angle measurement, which is the 60, because the hypotenuse gets the bigger of all of the angles, which is, of course, the 90-degree angle. Okay, so your short leg, long leg, and hypotenuse are positioned like that, and all of these lengths are based upon the short leg, and here is the connection, or here are the connections. In a 30-60-90, the hypotenuse is always going to be twice as big as the short leg. So if your short leg is x, your hypotenuse is going to be 2x. And the long leg is always whatever the short leg is times the square root of 3. So in this case, if your short leg is x, then your long leg is x times square root of 3. Okay, and as always, or as before was with the 45-45-90, okay, yeah, when you have one of the particular measurements, you just select the formula that gets you where you're trying to go, and you plug in what you know, and you solve for what you don't know. Okay, there's some examples worked out in those notes for that triangle if you need those as well. Okay, the next big rule that we got into with right triangles was, of course, the trigonometric ratios. Anytime we have a right triangle, we can use trigonometry. Okay, so we kind of discussed that we'd already seen a whole bunch of rules going on inside of triangles, but the bottom line here is just like with Pythagorean theorem. If you're going to treat a Pythagorean theorem in order to solve missing side length on a right triangle, you better have a right triangle. Okay, same thing with trigonometry. If you try to use trig on a acute triangle or an obtuse triangle, you will absolutely get an answer out of your calculator, but your calculator does not know that you did not have a right triangle, so it's going to give you a number, but it's going to be an incorrect number. So bottom line is no right triangle, no trig. Okay, now trigonometric ratios are going to need an acute angle to work with. Now, please don't get confused. You have to have a right triangle, but the right angle is not the angle that we are looking at from the trigonometric perspective. Okay, you should remember that all triangles have two acute angles. Okay, and a triangle is classified based upon what that third angle is doing. Well, in this case, our third angle is a right angle. That's why we have a right triangle. But anyway, we're going to come across some new vocabulary here based upon the positioning of the acute angles and the sides that are in the triangle. Now, of course, the hypotenuse is the hypotenuse. He's across from the right angle, and he always will be. Okay, but there are two other angles in the triangle that are not right angles. They are acute by definition. Okay, we can actually use either one of these angles as theta. It's completely up to us to decide which one we would like to use. Typically, one of them is provided for us, so that's usually the one that we're after. Okay, but whichever angle you decide is going to be the acute angle theta that you are going to work with, okay, the other two remaining sides of the triangle are going to be named according to their position relating to where your theta's position is at. Okay, the hypotenuse is the easiest one to identify, so I always recommend that students find the hypotenuse first. The second one that is probably the next easiest to identify is what we refer to as the opposite side of the triangle. And it's probably the easiest to identify because opposite in this case means pretty much the same thing that it means in the English language. It is on the opposite side of the triangle from where your theta is. Okay, so you can see at the two triangles at the top, depending on where your theta is, opposite moves from one leg of the triangle to another leg of the triangle, but in both cases it is opposite of the theta angle measurement. The third one to identify is usually the toughest for people because we're not all that familiar with the word adjacent. Adjacent means next to. Okay, so we are talking about a side that is next to our theta. The problem is there are two sides that are next to theta, no matter what, because it takes two sides of the polygon to build our angle. Okay, but of course, one of those sides is the hypotenuse. That's why we identified it first. Okay, so the third remaining side of your triangle has got to be what we call your adjacent side. You've got to get these guys named correctly because the trigonometric functions are based upon this naming system. Okay, now the word that you have to remember is SOHCAHTOA, S-O-H-C-A-H-T-O-A. It is imperative that you remember the correct spelling of this word because it is actually an acronym. Each of these 9 letters stand for something, and the thing that it stands for is actually the mathematical equation that we're going to be working with the trigonometric ratio. So if you misspell this guy or leave something out, you are most likely going to set up an equation that does not make any sense and quite possibly get the wrong answer. Okay, now we broke down the SOHCAHTOA as 9 letters, but is actually more specifically 3 groups of 3 letters. So the SOH is one group, the CAH is one group, and the TOA is the third group. The first letter of each of these groups represents the trigonometric function that is being represented. The first group starts off with an S. S is for the sine function. The second group starts off with a C. C is for the cosine function. And the last group starts off with a T. That is for the tangent function. Okay, the remaining 2 letters in each of the groups actually represent the ratio that belongs with this trigonometric function. The second letter in each of the 3 groups is the numerator of that ratio, and the last letter is the denominator of that ratio. And as you can see, all of the O's and H's and A's, those, as you probably guessed, were opposite and adjacent and hypotenuse. Okay. Now, each of the trig functions needs the theta angle measurement to go along with it. The trig function is actually a mathematical operation, and it does not make any sense without having a number to perform its operation on. It's like a plus sign or a minus sign or a times sign or a radical or any other thing that we've worked with. It needs a number to go with it in order for it to make any sense. So we're going to use whatever our theta angle measurement is. You have sine of theta, cosine of theta, tangent of theta. That will occupy one side of an equation. Okay, so your trig function and your theta angle measurement, they belong together, and then you get an equal sign. The other side of the equal sign represents the ratio that goes along with the trig function. So in sine's case, we have O and H. That is a numerator and a denominator. That is opposite over hypotenuse. In cosine's case, you have A and H. That is adjacent over hypotenuse. Tangent has O and A. That is opposite over adjacent. Okay, so SOHCAHTOA, SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you can remember that information, then the rest of this is not too terribly difficult, but you absolutely have to get the setup correct or you're going to miss the answer. Okay, so we spent some time trying to identify our ratios. Then we came back the next day and actually put the ratios into play. And what we basically learned here was anytime you have, okay, 2 out of 3 pieces of the information. Okay, you notice all of the trig ratios have this in common. They contain an angle measurement. They contain 2 side lengths. And just like any other equation in mathematics, if you can plug in numbers everywhere except for one location, you can solve for the missing location. Okay, so we went through several examples and looked at that. So if you have having trouble doing the math of it all, you probably need to look back at this lesson. Okay, I'm going to take one moment and just remind you that your calculator is capable of comprehending what the sine function does, what the cosine function does, what the tangent function does. Okay, the only catch is you need to make sure that your calculator is in the proper angle measurement settings. Okay, there's more than one way to measure an angle in mathematics. The calculator needs to understand that we are actually measuring our angles by degrees. So in the mode menu, you have to make sure that the little black highlighted bar is actually covering the degree mode, because that's not the default position of the calculator. The default position of the calculator, every time it's reset or the batteries are changed or anything like that, it's going to reset to radians. Okay, so you need to make sure it's on degrees before you do sine of your angle measurement or cosine of your angle measurement or tangent of your angle measurement, because it will give you an answer. It just will not be the correct answer. Okay, so as I said, there were several examples worked out in the notes. Okay, and the next day was just more of the same. The first day, basically what we did is we looked at only cases where it was a side length missing, and the next day we came back and said, okay, what if it's an angle measurement that is missing? Well, there's a new step of math here, because as we already said, the angle measurement, theta, and the trig function belong to each other. Together, they are a single value. So the question is, how do you separate the trig function from the angle measurement if they actually belong together? Well, if our angle measurement is a variable and we have to solve for that variable, you have to get the trig function to leave the theta measurement alone. And the opposite of a trig function is what we call its arc function. We should know well by now that anytime we want to move something from one side of the equal sign to the other, we have to do the opposite of whatever's already being done. So if you have sine that is being done and you need to stop that from happening, then the opposite of sine is arc sine. Okay, and it's abbreviated with the little -1 exponent looking guy just to the right side of him. The opposite of cosine is arc cosine. The opposite of tangent is arc tangent. And just remember that, of course, whatever you do to one side of an equation, you must also do to the other side of the equation to keep the equal sign balanced. Okay, just like you're seeing there. And you should be able to come up to your answers. But once again, anytime you push sine, cosine, or tangent, you better make sure you're in the right mode. The calculator will lie to you, and you most likely will not realize that it's happening. Anyway, that is all the information that we had in Unit 5. kind of a crash course in right triangles. We've seen some other stuff as the units have rolled by, but this was the bulk of it. Okay, anytime you have a right triangle, you have Pythagorean theorem, you have SOHCAHTOA, and if it happens to be a special right triangle like a 45-45-90 or 30-60-90, you got a couple of extra rules that can help you out as well. Anyway, that is all. We'll see you in class.